So I'm going to do a little video here about group actions. This is a really important thing. Your book doesn't quite talk about, well, at least in the chapters we're in, it doesn't quite talk about general group actions. There's kind of various notations here for group actions, and I'm going to stick with this kind of notation. Well, I mean, let me say something here. So generally an action is a map from G cross X to X. Okay, so not G in every place, right? So like the operation on the group is G cross G to G, right? And the group actions that you've seen used so far have also been G cross G to G. And so there, for example, the action GH or the action GH inverse, right? And this one was important, for example, in counting cosets, and this one is, conjugation. And so important things, but it's not always G here. Sometimes it's just a set X. And so our interesting application below will be that specific thing. And in terms of notation, we like to think of it like an operation. So think of it like an operation on X. So we'll write G dot X in place of this more complicated phi G X. Okay. And the property we have here, what this phi really does, and there's some useful reasons for thinking about it like this, because if I think of phi G as a map from X to X, right? So where I have phi G of X is equal to phi G of X, so we're sort of taking slices in a way, right? Then part of being an action says that the map, so what does this do? So this makes a map, G goes to phi G. And part of the axioms here is that this is actually a homomorphism from G into the permutation groups of X, right? So this map here, so this map G goes to phi G is actually a homomorphism. I'll just do it with a capital phi. So you can ignore all the letters if you want, but basically going from G to SX, right, is the way this works. And so formally the way this works out, so again, now using this notation, right, in order to say this, what I'm going to say is this, that if I do G, and then acting on G prime, acting on X, then this is actually G prime, right, acting on X, right? And so what this turns into, so we're doing this for every X. So if you think about this notation up here, this says that phi of G prime acting on X, right, is actually phi of G prime acting on X, right? And so this is saying that phi of G composed phi of G prime is phi of G prime, right? So this is like the automorphism, right? We're taking the group action, or sorry, homomorphism to composition, right? In the sort of symmetric group over X, right? Let's see, the other axiom we need here is just that phi, and this is part of being an part of being a homomorphism, is that phi of E, right, needs to be the identity map, right, on X, right? So the way we write this is that E dot X, or E acting on X, right? And E may be 1 or 0, it depends on the group, right, is just X, right? So that's the thing. Good, okay, so that's sort of the main bit of stuff here, okay. Okay, so let's see, then there's a little bit of talk here. So let's see, so I sort of said that. Settle this. Oh, sorry, I do right and left actions here, and I'm not going to talk about both of those here. I'm just going to talk about here the actions I'm doing are left, right? I'm acting on the left, right? So things are sort of composing on the left. Both actions are important, but here I don't want to do a huge bunch of this. I just want to do a little bit. There are some really important notions here. So if I take G, all of G and act on some X, right? The other way I could say that is I look at the set of all G, actions of G on X for G and G. This is now where X is fixed, right? So we have a fixed element of X. And so this thing here is called the orbit of X. Okay, so this is an important notion. And then we have this thing called the stabilizer of x. And so this is the set of all g such that g, when it acts on x, just gives you x back, right? So the things that just fix x, right? So here's an important thing. The stabilizer of x is a subgroup of g. Okay, so that's one important thing. The other important thing here is that the orbit, I'll write it like this, the orbit of x in terms of its size is actually equal to the size of g over the stabilizer of g. Sorry, the stabilizer of x, right? So this is the set of, let's say left cosets, right? So this is, this is the same as the size of the set of all g stab x for g and g, right? So the set of left cosets, we're doing a left action, we have left cosets. And the point here is this, that if g maps, if g dot x equals g prime dot x, right? So we have the same thing in the orbit, right? We're looking at two different ways of sending x to the same thing in the orbit of x, right? And this happens if and only if, g prime inverse g dot x, right? Which is of course, well, is equal to x, right? Because I'm just canceling out, right? So this is equal to x, right? So, g prime inverse g prime dot x is the e dot x, which is just x, right? And then g prime inverse dot g dot x is g prime inverse g dot x, right? So we're using the axioms up there. And so this is if and only if g prime inverse g is in the stabilizer, of x. And so this is if and only if, g stabilizer x. And we've seen this from looking at left cosets, right, is equal to g prime stabilizer x. All right, so we kind of, I don't want to say an isomorphism, but we get a one-to-one onto mapping, from the left cosets to the, this is a bijection one-to-one and onto, right, onto the orbit. Okay, so that's important. This does tell us also that that this number here doesn't depend on which representative of the orbit we choose. By the way, that's another thing, and I guess this is sort of clear, is that so the orbits partition x. So you have kind of two different sets of partitions here, partition x, right? So the left cosets, of course, partition g, right? But the orbits themselves partition x, right? And one way to do this is see that if we defined an a relation x, equivalent to y, if and only if there exists a g in g such that g dot x is y, right? So those are the orbits, right? Then you can check easily that this is an equivalence relation. And so the equivalence classes, of course, are just the orbits, right? So we get that. And that tells us that this number is the same no matter which representative of the orbit we choose. We actually might want something a little stronger than that. So notice that if g x equals y, right? So I'm taking a y which is in the orbit of x, okay? And let's say that h is an element of the stabilizer of x. Then we can do this computation here that g h g inverse, okay, so there's a thing dot y, right, is g h g inverse dot g dot x, right? That's because y is g dot x, right? Have a little dot there. And so this is GH. Now we're using two things. We're using associativity in the group, and we're using this kind of associativity for the dot, right? So dot G inverse G dot X, right, like that. And so this, of course, is GH dot. Now what is this? Well, this is, well, I'll write it all out carefully. This is EX, right? But E dot X is just X. So this is GH dot X, right? So this is G dot, H dot X, right? But H was in the stabilizer, right? So this is equal to, this is just equal to x, so this is g dot x, and so that is y, right? So in particular, the conjugation of a stabilizer element by something that maps g to y, right, is actually a stabilizer element of y, right? So we get that this map, right, so the map h maps to g h g inverse, so this is conjugation, right, is an isomorphism from the stabilizer of x isomorphic to the stabilizer of y. Okay, so so we have more information than just that these two sets have the same size, right? They're sort of very closely connected to each other by that isomorphism there, right? Okay, and you can imagine there's lots of counting stuff that happens here, right? So we know that x is now broken up into these orbits, right? So the size of x will be the sum of the size of the orbits, right? So O and O, these are all the orbits. I can't just range over x because I don't want to double count things. I just want to throw the orbits in once, right? And then this is summation, the size of g over the stabilizer of x, right? Where x is in one of these orbits, right? Doesn't matter which one. That's what we just showed. That number doesn't matter, right? So maybe we should associate some number to the orbit that's the size of the stabilizer, right? I don't know that that has a name. But notice one thing is like these stabilizers all, for example, divide G, right? So, and X has the same size as this. So the only divisors, so if something's dividing G here, and it's not being divided out by one of the stabilizers, then it divides X, right? There's all sorts of things we'll use here. To count things in X, right? I mean, we won't do so much with this, but if you're going to do the silo theorems, for example, it's really important. We're going to do one really important example, one really nice example that strengthens something your book does. So there's that relation I had there, and here's the application I want to do. So the application I want to do, let me just write down the application first. So it's called Cauchy's theorem. Your book has a version of this that's weaker. And it also, I mean, this is a really cute proof that we have here. So this just says if P divides the order of G, so I'm not making any assumptions on G being abelian or anything, right? Then there is G and G with the order of G, so I can find an element of order P and G, right? So I can find a subgroup of order P for any prime that divides the order of G. And we don't need to worry about G being abelian. So your book has this theorem for G abelian. And so there's lots of things here, but one thing of this will be a completely different proof, right? So, and it's sort of a cute, it's a really cute proof, I think. Okay, we need one definition here. And again, so one of you is going to look at the silo theorems. And so this is one of the things you'll have to look at too. If I take an X and X, that I'm going to call, I'll say X is fixed by the action, now I say the action, so assume I have some action. And again, here I'm just assuming I have left actions if and only if g dot x equals x for all g. So what is that saying? That's saying that, this one way of saying that is that the stabilizer of x is just all of G, right? And of course it's also, so that means that G over the stabilizer of X, and this is just the size of the orbit, has size 1, right? So this has size 1, right? This is the size of that orbit, right? So in particular, when we look at this way of breaking X up as the summation over the orbits, right, of G over the stabilizer X, right, like that, this equation I had above, I can kind of break these into two parts. So this will be over, so part of it will be the fixed elements, right? So I'm going to call this fix Okay, so it's just going to be the set fix, right? So fix will be the set of all x such that x is fixed. So it's fixed by everything, right? So of course, each one of these orbits has size 1, right, for that, or not, yeah, each one of these orbits has size 1, right? So this is a bunch of like 1 plus 1 plus 1 plus 1 plus, right? And then we have summation O and, those things minus fix, right? So for everything else of this form, G over, the stabilizer. And the point is this, right? If G is a P group, if G is size P to the N, right, then all of these things have size P to the K for some K, right? Because it's the only subgroups you have are powers of K. These aren't one, these aren't one, right? So they are divisible by P, right? So in particular, what we're getting here is we're getting that, P divides X minus fix, the size of the fixed things, right? So the number of fixed elements, right? Like that. So if we want, we can write this as fix is equal to X mod P. This is whenever G is a P group, so when it has size P to the N, right? So this is what we'll use here, okay, in the proof. And so here's how the proof is going to go. It's really cute. It's written down right here in case I mess something up along the way. So here I'm going to have, so I want to prove that every group of order, this divisible by P for some prime, right, satisfies that there's an element in there where G equals P. And so what I'm going to do is I'm going to look at this set X. So this is not a group. I'm going to be acting on a set. This is going to be the set of X1 through XP. This is the cute part. I mean, I don't know. Who would have thought of this? So it's just X1 through XP equals E. Right, now what I'm looking for is I'm looking for something where X to the P equals E, right? And and X isn't E itself, right? That's sort of the point. Good. All right. And we're going to have an action of ZP, not of G, but just of ZP is going to act on X. And the action is going to be, so if I take something in ZP, so M dot one of these things is going to just sort of rotate through here. So let's see, it probably doesn't matter which way I do this. I'm going to push, let's see, let me think about how to say what I'm doing here. Yeah, sorry, I have to think about it. The indexing is the only thing here, right? So what I'm doing is I'm rotating through by m many things, right? And so the indexing works out like this: p minus n plus 1 up through x p, right? And then up here I've got x1 through x p minus m p minus m, right? So I'm just sort of rotating around here, right? Shifting by m many spots, if you like. And then sort of when things fall off the end this way, they come back around to the front, right? So that's the idea. Okay, and so we know that fix, so that's the action, right? And fix does have at least one element in here because this thing, E, right, is an element of fix, right? What other things could be element of fix? Well, if they're going to be fixed, right, no matter how I move these things around, I'm always getting the same sequence, right? So the only other things in fix would be things of the form xxxx, right? P many times, right? So, if this thing is in fix, I mean, maybe I should write like this. If x1 through xp is in fix, then x1 equals x2 equals, through xp, right? So in particular, I would have that x to the p is equal to e. Remember, those are the things that are in fix, right? So these things, yeah, so these would have to all be the same. And, right, to be in the set, right, x to the p is equal to e, right? Sorry, let me write this so we can read it. I'm sorry, erase, oops, okay, right, come on, erase. Okay, so this thing is in fix. Let me give myself some more room. Okay, so let's try that again. So, oops, x1 through xp is in fix. All right, so first of all, this thing has to be in the set X, right? So if and only if, so X1, X2, you know, the product, XP is E, right? That's being an X, and, right, all cycling through all these things have to be the same. So in fact, X1 has to equal X2, has to equal, you know, all the way through XP, right? So this is if and only if X to the P is equal to E, right? And of course, this is what we're looking for. We're looking for one of those things, right? But what do we have above is we have that the size of X, right? Let's actually, let me write it the other way around. So I have that the size of fix, right, is equal to the size of X mod P, right? So that's what we had above, just from our general analysis. Good. So like, what is the size of X, right? So if you think about it, when I pick through xp minus 1, right, from G, right, I can just pick this last thing, xp, right, it needs to be the inverse of those things there, right? xp equals x1 through xp minus 1 inverse, right? So there's no option on how to choose this. It's got to be the inverse, but there's complete freedom on how to choose this, right? So the size of x is definitely the size of G to the p minus 1. That's the size of X, right? Now, it's not a group or anything, right? There's no group structure in X. It's just a set, right? But in particular now, P divides G. That's one of our assumptions, right? So P divides the size of X, right? But what does that mean? That means P must divide fix, right? So in fact, not only do we get that there's a thing in fix, but we actually get that there's at least, you know, p minus 1 things in fix, right? We know that fix is definitely equal to kp for some k greater than 0, right? Because we know it's got something in it. It's got right, in there, right? So it's definitely got some elements. We didn't just show there's one element. We showed there's actually several elements, right? But we're getting, you know, some elements, you know, of order P in G, right? And we're doing that by looking at an action of ZP on these tuples, right? So very interesting, I think, very sort of a fun, interesting proof of this thing. I'm sure there's other proofs of this thing too, but this is a nice proof of this thing using actions. Good. Okay, so that will be what I'm wanting to do here. I guess just to say there is a stronger version of Cayley's theorem, and I'll let you read this. I would like to say something better here. I would like to say that I could use the sort of the Cayley graphs in a natural way, but anyway, it's just kind of hard to say correctly. Anyway, that's what I'm doing for now. So let me see, let me pause this.